So now that Peter has told you all about voxels, I'd like to talk a bit about how these might be combined with satellite data. And bringing these two technologies and two types of data sets together, I think could provide some really interesting outcomes and additional products. So I'm Brian Killough. I work for NASA, but my full-time job is with this organization, CEOS. So the Committee on Earth Observation Satellites, we're a group of civil space agencies around the world that work on collaborative projects using satellite data. And there's a number of different things that we do, but we have 163 active satellites, 61 agencies, 23 countries. It's quite a diverse organization. And one of the things that I've jumped into in the last few years is the technology of data cubes and how to take some of this satellite data, make it easier to use, and bring it together with things like VoxelMaps. So there's a number of trends that we're seeing in the satellite data world. And some of these might be obvious to you, others may not. Let me hide this floating panel. And the first, I'll start off in just saying that all of this data is now available in the cloud. We're seeing Amazon and Google and Microsoft, the big US groups that are taking this data from the satellite agencies and making it available in large volumes. So we're finding ourselves not downloading the data. It is becoming a trend in a very large way. People are no longer downloading this data. They're actually taking their analyses into the cloud. They're also pre-processing this data into analysis-ready data format. So that means that the user doesn't have to take things in this level 1 data format, go through complicated processing and get it ready. It's already ready for them. And along comes this idea of the Open Data Cube. I'll tell you a little bit about that on the next chart, but this new technology allows us to rapidly bring different data sets together from different sources and to utilize this in a data framework. So if you don't know Python, you probably should go learn some Python. It is just amazing how that computer language has taken over most of the way that we interact with satellite data. Working with some students even this week that are starting a summer internship. And what's the first thing they're going to do is they're going to go and have a little refresher course on Python and start to dive into some of our Jupyter notebooks. So the environment for working with this data requires Python. We're seeing that as a big push. The international collaboration, our Committee on Earth Observation Satellites, and the UN groups with the Sustainable Development Goals are really pushing this international collaboration, and that's a big thing. Radar data, not since 2017. That is when we have a large, consistent volume of radar data that's free and open to everyone coming at us from Sentinel-1 and the Copernicus program. Prior to that, it was almost impossible to get radar data. Very expensive, not really publicly available anywhere, and now we have it. I don't think a lot of people use it. Very few people use it, matter of fact, and I think there's a big trend in a movement towards using that. And then finally, these other and new data sets. We see it here today with the Earth project, and I think that you're going to see LiDAR data in the form of voxels. We're seeing drone data, different data like night lights. There's a lot of interesting data sets that are out there. So let me tell you a little bit about this thing called an Open Data Cube. It's an open source geospatial data management system, but the idea is that we take the satellite data sets, we put them in a form, and we organize them in a database in such a way that we can interrogate that data very efficiently and effectively, and then through APIs, we can produce algorithms that you see on the far right of the screen. If you want to learn a little bit more about it, hop on to our website at opendatacube.org. There is a large number of people now using this data infrastructure. It's being used in 100+ countries around the world. It has really become quite popular, and we're excited to see that it's gone that direction. And a lot of this is because it's open source And we, from the very beginning, decided that was the direction we wanted to go. So prior to this year, what started all this, the Open Data Cube technology was invented and proven in Australia. That's where everything began for this project. And then we within the CIOS organization looked at that advancement and said, could we take this and make it readily available to other people in the world, open source all of the core code and the applications? And that's exactly what we did. So a number of us, Geoscience Australia, CSIRO, NASA, and USGS came together and started to push this out. We started a demonstration project in Africa called the African Regional Data Cube with 5 countries. That went really well. And that soon led to Digital Earth Africa. If any of you have heard about that project, quite a large project. It's a continental scale data cube for all of Africa. Since that time, I've been recently working quite diligently with the Pacific Islands, where there's soon to be a Digital Earth Pacific coming about. The South Pacific Consortium is going to be leading that. We're also in some early planning stages of Digital Earth Americas for the entire Americas region. So there's a lot of regional data cubes that are starting to pop up and take hold of this technology and utilize it. So as I said, 100 different countries are impacted, and we're seeing a lot of application algorithms come out of that, some really interesting cloud computing methods and AI and machine learning and all the things that you're probably familiar with and will hear about in these 2 days. So in the future, our ultimate goal is to have a global network of these regional data cubes, as well as the application algorithms that go with it. And if we're able to grow this community of users, share these algorithms and be able to test them and to bring them together, then we think there's a great potential to demonstrate impact for sustainable development goals and then other projects just like yours. And so this particular project with Earth Archive, I think, is a very unique and different one. And it's something that could have a larger impact. So I want to talk a little bit more about how we're going to try to connect this data to the LiDAR VoxelMaps and some ideas about where it might take us and what we could do with this. So we already heard from several presentations this morning that this LiDAR data has many applications. It's been traditionally used for digital elevation models. We can look at land surface deformation, so they look at ice sheets quite often, vegetation canopy. All these are things we're quite familiar with. But most of the data sets that we have that are readily available out there in large volumes and public sources, they're fairly coarse in resolution. They're 30 meter, 90 meter. These are the way that we get a hold of them. We don't necessarily see the high resolution data sets, at least in a free and open context. But those data sets don't give us that structural detail. Everything that you saw in Peter's presentation, getting to the detail of the trees and understanding the vegetation and the underlying ground infrastructure and surface height, none of that's available with a typical DEM. And so, and not to mention it's at specific and infrequent times. If you go back to SRTM, that's early 2000s. And then the most recent Copernicus data set is around 2015. So how do we get something that's 2021? Or what if we're looking for potential changes in the last 6 months or a year? We're going to have to measure the ground more frequently. And that's where I believe Earth Archive and these new types of measurements come in. So big advantage is the higher resolution. If we can get down below 25 centimeters and into the single digits of centimeters, it's just incredible the amount of information we now have available. We can learn a lot about the three-dimensional structure of that vegetation, and it can give us a lot of information for things like land classification and carbon accounting. I'm always amazed at when we look at images of the Earth and we try to decipher the land classification. We don't do a great job. 80 or 90% is considered a fairly good land classification model. And I believe with this kind of data, we can be much, much better because that three-dimensional structure is going to give us that extra piece of information that is likely going to lead to a very high quality classification. Not to mention carbon accounting. What is that thing we're looking at? What kind of tree? What is the density of that vegetation? And all of that is key to carbon accounting. So we heard that the Earth Archive data is going to be put in VoxelMaps, and it's a volumetric model of the surface area. So imagine now if we take Peter's VoxelMaps, and I'm assuming they'll be in a cloud somewhere, readily available to all of us, free and open, and he hooks an API to that. I can now have a data cube sitting elsewhere on another cloud, tap into Peter's data in the VoxelMaps, and be running algorithms that bring all this together. That's the vision I see for where this can go. Peter and I have had some early discussions on this, and we're really excited about the potential of investigating how to bring these two data sets together. And then the other thing is this kind of LiDAR data can be acquired at more frequent intervals. We can do this at weekly, daily intervals and learn about land change. There could be things like hazardous storms and damage or land change that occurs at a much smaller time scale that is almost impossible to get out of optical satellite data that has clouds in the way. So there are other ways that we're going to have to look into the potential for this data. So I'm going to leave you with the last bit of this presentation, and that is, what could we do with the VoxelMap data and the satellite data, bringing this together? As I suggested, Peter and I, following this meeting, plan to connect our data sets and our ideas, technically bring them together so that we can connect satellite data with the voxel data and open source algorithms and bring all this together to demonstrate technically how to do that. The next step will be, what sort of algorithms and things can we do and products can we create by bringing these two valuable pieces of information together? I already mentioned land classification models. We have issues with validating even water extent boundaries. Imagine the detail you can get from a water extent boundary, because if we know all of the surface undulations, we'll know precisely where the water lays and those precise boundaries of the water. That's also very important for a lot of our classification models. Urbanization is another one. Understanding, am I looking at actual urbanization, or maybe I'm looking at something that is just a bare soil, bare land that's been misclassified. There's a lot of things we can get from this data, and then vegetation extent. If many of you have probably heard about the carbon accounting push and the things that are happening in the UN with carbon extent and carbon accounting. So all of this data will be very important to learning more about how we can do that with more accuracy, and perhaps getting to those solutions in an efficient way and for everybody to share. Something we do in one country or one location, to be able to share that with others, because it's all open source data and open source algorithms. To me, that's the exciting part of where this is headed. And I'll end with the last question is, what ideas do you have for using this data? Peter and I would love to hear about them, because that, I believe, will drive us to testing out some ideas. So anything you can bring to us will be exciting. Thank you.
Thanks, Brian, for that amazing talk. And Peter, I don't know if you want to turn yourself on here for this stuff, because we do have a bunch of questions. A lot of it centers on, I'm just going to try to summarize these a little bit. A lot of it centers on computing efficiency, computer requirements, storage efficiency. And I'm wondering if maybe both of you could, maybe we could, you guys could talk a little bit about those topics from your sort of disparate perspectives, and what we might need for that, and where you see that maybe going, if that makes sense.
Sure.
Peter, why don't you go? Your pixels are smaller than my pixels.
Yeah, so it's a really good point. Sometimes when I talk about this, a lot of people are saying, why hasn't this been done before? And really, up until a couple of years ago, there just wasn't enough compute power at the right kind of price to be able to make this happen, and storage as well. So obviously a voxel model of the planet is big. There's no dispute in terms of that at all. But totally achievable. And so the way that we've structured it at VoxelMaps is that we now have a private cloud, which has very high performance computers, lots and lots of NVIDIA graphics cards, which are processing, voxelizing, and performing the initial analysis. And then the production version that's ready is then pushed out to a public cloud like AWS, and it resides there for everybody to have access to. But really what we're starting to see, and by the way, in the city model, we're actually doing this in real time. We actually have a project where we're taking the data collected by these mobile mapping sensors via 5G and processing it in 15 seconds. So from collection to actually usable data, 15 seconds delay. So that kind of capacity is starting to exist. But still, for some applications, the data might be a little bit too heavy. And so that's why we vectorize the data as well. So, we can pull off, almost the voxel data is like a data abstraction layer. And then you can pull off the data for different applications in a much lighter weight format as well. And so we kind of facilitate all of that, really.
Yeah, our data, most of it is probably smaller, perhaps in volume, and less complex than the data that Peter's talking about. We're storing things in 10 meter and 30 meter type pixels. And yes, it's a large volume because it covers the whole Earth, and we're talking many terabytes and up into the petabyte volume. But as Peter suggested, the computing technology we have now makes it extremely easy to access this data. And I can run analyses just so quickly. It's just amazing. In a matter of minutes, I can pick a region of interest, run a fast analysis, find a non-cloudy scene, and produce a product in just a matter of minutes. And I remember a story in Africa when we taught some people how to do that. And I did a demonstration once that took about 5 minutes. And the man was from Africa was just astounded, and he stopped and he said, "What you just did would have taken me 2 months to do." And we did it in 5 minutes, but it was all because of the computing power.
Yeah, absolutely. And that whole insight piece, actually what Intel was talking about before, Vijay, the application of artificial intelligence to the data is absolutely key, changing it from data into insight. And you're starting to see more and more of that. And definitely as computing power is increasing, it's just feasible to ask questions and create models which just have never really been done before. And that's why it's exciting to have the opportunity to talk to other academics and scientists and find these problems and say, okay, we don't know if we can solve all of them, but maybe we can. maybe we can go a long way. So let's try it.
I see there's a question. There's a Q&A in there. If you want me to take a hack at that, has to do with tracking the migration of people. And I believe the short answer is yes. Why not, right? If we can see all the things that you showed, Peter, at that small of a scale, we can certainly know where people are migrating to. New villages are being formed. We're seeing some of that in Africa, and I've been asked that question before. The problem is with 10 meter and 30 meter satellite data, I might get a general idea of where people are moving, but the data, a lot of times it's optical. I've got clouds in the way. I've got issues with deciphering what am I looking at? Is it bare soil? Am I looking at a new building? But if we have the detailed volumetric data that we're talking about with the voxels, we can bring that together with the satellite data, and we can find out things. Well, oh, look what's happening. They're devegetating this area. They're moving in, they're constructing new villages, and now we know precisely where they are and the timing of that.
Yeah.
Fantastic application.
Absolutely. And it is this whole concept of merging this data together and being able to ask those broader questions and seeing where the resolution really exists to be able to get, to pull back that insight, really.
So I also know that Devin White, archaeologist, and he works for he was at Oak Ridge, I'm not sure he's there anymore, has a model that he developed for his dissertation called FETE, F-E-T-E. And it's like least cost path analysis on steroids. And it's really, really fascinating. And I know that he has been working governments and other people to look at where the optimal migration patterns might be across borders and things like that. And it would be interesting to pair that model with some of the LiDAR data and actually see if, maybe we can see people or see evidence of people. And then also, another application is animal census. So in Africa, one of the big issues they have is, counting. One issue would potentially be counting elephants in forested areas. It's really hard to see the elephants. And if you're now able to pick out individual trees, you can certainly pick out something like an elephant or something like that. How much of the world would you guess VoxelMaps has already mapped? Well, Peter, I'll let you.
Yeah, sorry. So we're very much in the beginning stages of that. So we're very focused on the US at the moment. So we're mapping the whole of the US over the next year and a half in terms of cities, really. And then it's with partners in other countries that we're either deploying the technology or becoming a technology provider to ingest the data, for that. I mentioned mapping the world is a huge task. No one company, even if you're huge, can really afford to do that frequently. And so it is really about working with other partners and other organizations.
And then Peter, there's a question here that's probably closer to your heart than mine. One application is an accurate mapping of the extent of the loss of greenbelt land, forest land, and agriculture to urban development currently occurring around London. I don't have a London connection, but you certainly do.
that would be really interesting, actually. So if you can tell from my accent, originally I am from London. But yeah, there'd be lots of questions like that, both from, the Maria data was interesting. That was obviously a natural disaster, but it had a big impact, obviously, on the forests and the trees there. But obviously human encroachment and, the impact that the cities and urbanization is having as well. So again, all of these are great questions. We just need the data, and then we can start applying the technology to it.
So let's do one last question, and that has to do with data fusion, different sources, and some advantages and disadvantages maybe with the voxel format. I'm sure Brian, you could might have a comment.
Well, you're talking about the last one here with the data resolutions, the merging of the data. I think Peter, you addressed that a bit in your presentation. You might want to expand upon how do you take something that's in centimeter scale resolution in a voxel map and now relate that to a 10-meter radar pixel or a 30-meter Landsat pixel? What are your thoughts?
Yeah, absolutely. So actually the whole voxel model, and I didn't dwell too much on this, but the matrix is this multi-resolutional voxel model. And so at every point, there's different size voxels, you just can't see them. And so they all relate to each other. They're all configured in something called an octatree. And so we have the ability, for example, if you have data that's 10-meter resolution, we can represent that as 10-meter voxels. And we can literally slide up and down the scale. So the visualization can be interesting because, if you're using coarser data and you want to visualize it with finer data, you have to put, transparencies on in terms of visualization. But the data sits, perfectly together. And so as long as we can generate essentially points that we can then convert to a voxel, it doesn't really matter then the resolution of the voxel.
That'll be some of the testing we plan on doing, which would be to take some of this high resolution voxel data, collapse it down into something that's compatible with the satellite data, and then start to bring those two together and say, well, what is one saying versus the other, and how can we relate them for an application?
And we already do this with radar in cities. So we actually create radar maps of cities. And with radar, you just don't get the same resolution as LiDAR. And also radar passes through some, objects, so it looks a bit different. But that's in the same data set, we can have the LiDAR map and the radar map existing. And we can even merge those two things together as well. And so we normally do that around localization for autonomous vehicles, for example. That's one of those use cases.
And we're out of time, and I would love to continue this conversation. And hopefully, some point we'll all be in the same room with some beers, and we'll be able to actually do that. And this is awesome, I think game changing.